So this automation lunch and learn is going to be pretty short. This one is going to be on how to do the ISO IEC 17025 measurement uncertainties in metrology.net. The learning objectives here always is going to be we want to reach into some of the object-oriented programming principles. We're going to talk about how the drivers are doing their measurement uncertainties. And you can see in the code how they come in and do their calculations. We're looking at the resolution and repeatability, how the drivers will add that back into the measurement uncertainty budget. Then we're going to talk about how you can come in and format an Excel spreadsheet to calculate your measurement uncertainty in metrology.net and use that as an alternative measurement uncertainty calculator from what the drivers are doing. And then we'll show you how you can upload that spreadsheet into the system and use it. So you all know that CalLab Solutions is a company that does automation. So we created metrology.net starting back in 2013, and we had it out as a project in 2015, and we were moving forward with doing more and more things with this. Automation is always about business efficiencies, doing things better, cheaper, and faster. And that's what we're trying to do in here. So a lot of companies will spend a lot of time doing their measurement uncertainty budgets. And sometimes companies, one of my customers right now is getting ready for an audit and going through an audit. So they're going to be shut down for 2 weeks going through doing their measurement uncertainty analysis, getting ready for the audit. So it takes about a 2-month process to prepare, go through the audit, and then take care of anything afterwards. So there's a lot of things that we need to do on our measurement uncertainties that's going to come back in and affect what we're doing in automation. I like to start in software with a problem statement. So here our problem is our automation software uncertainties and the lab's accredited measurement uncertainties. These things don't match. So a lot of times those are the problems we're going to have inside of a calibration lab is auditors who really know what's going on. They know where certain software is calculating uncertainties differently, and they're going to come in and say, hey, these measurement uncertainties that are getting calculated here, they are not the measurement uncertainties that are on your scope of accreditation, and you can get a major finding if they find you're putting out measurement uncertainties that are less than what's on your scope of accreditation. So part of what we wanted to cover in this is to show you how metrology.net calculates its measurement uncertainties, and then how you can integrate the same scope of accreditation uncertainties into metrology.net, and those two things don't have to be separate. So we're going to look at Fluke 5720's measurement uncertainties and how they're put into the test process source volts DC driver. You can come back in and see how it's going to add in, or how it's calculating its measurement uncertainties based on the manufacturer specifications, and then how we come back in and add resolution and repeatability, so we've got our total measurement uncertainty budget. So then you can come in and add your own spreadsheet and put that in there so you have an alternate uncertainty calculator. And the reason you would need to do that is because when we create the drivers, we don't know if your lab has done any kind of reproducibility study that you want to include in your measurement uncertainties. We can't put that knowledge into the driver, as well as the cal traceability that gets into it. Now, most of the manufacturers will tell you that their Type B specification is going to include the cal traceability when they specify the instrument, but they don't document that inside of their manuals, so some auditors won't accept that that's in there, and they'll require you to add in your cal traceability on top of your measurement uncertainty. So that's one of the reasons why some labs will have to come in, add in that spreadsheet so they've got an alternate uncertainty calculator, especially for their higher end calibrations. In here is a little bit of a code review, and people who are running metrology.net, they can reach in and see what's going on in the code. So this is out of the 5720 source volts DC driver, and you can see in here when we make a call to calculate the uncertainty, the first thing we have to determine is, are we a 5700 or are we a 5720? If it's a 5720, it's going to jump down to the 5720 call and put in the voltage. And once it jumps down into the call, you're going to see it here. I've just expanded this code out. You're going to see it here based on the voltage that's getting put in. We have a case select, and we're going to look at each one of the ranges. So if we're less than or equal to 0.22 volts, we're going to use this formula here for the calculation. and that's going to be the results that are returned. If we're greater than 1100 volts, then we're going to come back in and say it's 39E39. We don't know that measurement uncertainty. It's outside of our scope. The calibrator shouldn't have even let us set it up to ask for that measurement uncertainty, but just in case somebody asked for an uncertainty that's outside of that 1100 volts, that's what we're going to see come up. So the next thing we want to do when we're going to come in and QA things is we want to look at, is our select case doing what it says it's supposed to do? So in here you can see there's a comment that says we're using the 95% confidence 1 year interval. Pulled this out of the 5720 manual, and this area highlighted in red here, you can see those numbers are matching. So you can see we've got the 0.75 parts per million value, and 4 microvolts or 0.4 microvolts is what we're going to put in there. So you can see each one of these is going to convert it to the microvolts or the parts per million. So our 7.5 times the voltage times parts per million is going to give us that uncertainty. Then we're going to add to it the 0.04 microvolt. So you can come in, open this up, and QA these values back and forth between what the manual says to see that we're calculating our measurement uncertainties correctly. One of the updates we want to do in the future is to make these things selectable. So you can come in and say, I want to use my 90-day, 180-day, or 1 year specifications, and I want to use my 95 or 99% confidences. So we want to add that in as an upgrade in the future to where you can come in and just select the measurement uncertainties you want to run. So now once we've pulled out the measurement uncertainty, and you can see here with this line of code that we're grabbing the test results, we're asking our source measurement, giving it our parameters, and it's going to pull back our uncertainty. So we're going to make a call back to get our measure end, and it's going to pull back the value that it was set to and the measurement uncertainty. So when we're using a 5720 and we're setting the resistance value, and we want to get the current resistance value of the calibrator, this is the callback that we make, source measure and that will give us the uncertainty and the actual output value of the calibrator if we needed that. So because we're sourcing DC voltage, we don't have to ask it what its value is. We can see that getting stated. So as we pull this value back, it's going to come back in, and you can see we're in this loop. So we've got the reading that we're on, and we're going to do one to the number of readings. So we're going to take measurement after measurement after measurement after measurement. And each time we're going to save our results. And each time we come through the loop, we're going to add our measurement in that we have. So as we're running through the loop, each time we're going to add a measurement to our test process. And you can see that here. So our test results is going to add a measurement with the value, and then we're going to set the uncertainty that comes with it. So each time we're adding a measurement to our process, that's where we're getting that statistical value. So we're reaching in there, adding measurement 1, adding measurement 2, adding measurement 3. So we have all of our measurements, and we can come back in and calculate the repeatability of that measurement as well as the resolution based on the values that are put in there. So when we come in and run this save results, this is going to come in, and this is the code behind for the save results. And you can see how it's looking at the results, and it's getting the measurement repeatability. So if we've got more than one, then we're going to add in this parameter that's the repeatability, and the results object is going to calculate our repeatability and pass those values onto our measurement uncertainty calculator. Then you can see here this little piece of code is going to add any other parameters that were added to the results. So this add parameter, if there was some kind of a measurement, that's what's going to add that to the result. So you can see what the error was in the process. And then down here, this grab the resolution is actually going to reach in and grab the resolution of it. And it's wrapped into a try catch so that if we have a problem with the resolution, we don't fail the code. So this gives us some ability to come back in and set a parameter for the resolution or grab the resolution out of the test point. So that keeps the code from breaking inside of there. So as the result gets saved up to the server, now you can see in here that we've got the test point. It had our voltage and our range, but this test result, this gave us our measured value, because we may want to use our measured value in our uncertainty calculator as opposed to our nominal value. And then we get the repeatability, the measurement count, and the resolution gets passed or gets stored with the result so it can get passed into the measurement uncertainty calculator. So the uncertainty calculator can come in and do those things based on the actual values, not any kind of model values. So now the way this works, when we're running source volts DC, we have our 5700 set up and we can select our measurement uncertainties that can be tied to that measurement process. So you see that it's a 57X, 57X0A is the driver, and it's going to support a 5720 or a 5700. And you can see right now I've got 3 alternate uncertainty calculators that are available for that. So what metrology.net does is it takes that measurement, it calculates the uncertainty inside of the driver, it posts that result back up to the server, then the server checks, do I have an alternate uncertainty calculator? And it's going to reach in and grab all of these parameters and pass those parameters to the uncertainty calculator at runtime. So you can get your measurement uncertainties without having to go in and do any modifications and touching to the code to get the uncertainties that you want to use for that calibration. So the way metrology.net does that, and it can grab what's off your scope of accreditation, is typically people are going to use something that looks like this inside of their spreadsheets. And this is a summary of the spreadsheet that gets pushed up there. And you can see they set back and calculated in the specifications, the resolution, the UUT resolution, the certificate of calibration, and the traceability. So each one of these values with their different distributions is embedded inside of this spreadsheet. And the spreadsheet is what you would hand off to the auditor to say, this is how I'm doing my measurement uncertainties. Now, you might have a different tab for each one of your ranges on your calibration and probably a different spreadsheet for each one of your calibrators. But you can take any one of those spreadsheets and you can come in and add this metrology.net tab. And you can think of this as an interface to how it's going to interface with that spreadsheet and pull those values back and forth. So looking back at the spreadsheet, you can see that there's a value here that we're going to grab, which is 4.4 E minus 5. And when we look at the spreadsheet that we're running, we're going to grab that summary G20. So we're going to grab that summary G20 and we're going to write that value back here. And that's what metrology.net uses to grab the value out of the spreadsheet and use it for its measurement uncertainty. So the way the system works is it's going to grab from our parameters that we have, it's going to grab the voltage that was set, it's going to grab the repeatability, the resolution, and it's going to fill out this spreadsheet, tell the spreadsheet to run the calculations and grab this value back. And then that's what it's going to use for the measurement uncertainties for that calibration. And it's also going to add a key into the database that says, this was the spreadsheet I used and the version of the spreadsheet that I used to run this calculation. So now to add a new spreadsheet up into the system, you're going to go over here to the Uncertainties tab, and you're going to click the New Calculator, and this little form is going to come up. So you get to name the spreadsheet, anything you want to name the spreadsheet. We're going to start with the version 1. The author of the spreadsheet I uploaded wasn't CalLab Solutions, it was Metrology ERP, and that spreadsheet is actually part of the package we give customers with metrology.net. You're going to give it anything on the method, so this is just a direct source, so that's a freeform text, and then you're going to select that you want a sheet. Then you click the Save button, and it's going to create you the template where you can upload that spreadsheet. So it's going to create the uncertainty calculator, and now you can come in and start doing the edits you need to do to your uncertainty calculator. So the first edit you have to do is you have to tell it the unit of measure that it's going to be associated with. In this case, it's associated with a voltage unit of measure. So that's going to be the quantity we're dealing with. And then from setting this voltage, it's going to populate this list of what measurement processes are in the database that are using that quantity. So you get a drop-down list, and here we're going to select that we want to associate this measurement uncertainty calculator with this test process, source volts DC 5720. Then we're going to choose our file that we want to upload, and we're going to hit save, and that's going to upload everything into metrology.net so we have that available. Once the spreadsheet is loaded, you're going to notice that the items that were in that spreadsheet become up here. So now you can set your voltage, set your repeatability, set your resolution, hit calculate, and it'll use that spreadsheet to calculate your measurement uncertainties. So now the spreadsheet is available, and it can be used for manual testing and auditing to make sure we have everything correct. But you have to approve the spreadsheet before it gets used. So now you come in here, you say, Mike Schwartz, you type in your password, and you hit save changes, and now that spreadsheet is tagged as an approved spreadsheet, so now you can use it. So the next thing you're going to see is now with that test process source volts DC, selecting the 57X, now you can see that that driver becomes available, that you can use that measurement uncertainty for that driver now. So it's completely available. So any questions on using the spreadsheets and with the automation?
So will you need one of these spreadsheets, a separate spreadsheet for each range of each of these test types?
Yeah, actually the way we put the spreadsheets together is there's a specifications, and it jumps through the specifications and it grabs the range value. So here's the spreadsheet. When we look at the specifications, the way the spreadsheet's set up is we've got one for each one of the ranges. So this is going to come in and grab those specifications for each one of the ranges, and then this is actually wired to pull different ranges. So if I come in and I set this to 200 volts, and you come in and look at the specifications tab, you're going to see that it used the 220 volt range, and then it populated this with a different value. And then the summary where it grabs the specifications, and it's just how this is put together, but this is going to grab that value off that specification page. So this is going to grab specifications H2. So it's grabbing specifications H2, so it's grabbing that value and pulling that value over. And then the same thing with the standard resolution. We selected a different resolution for the standard. And then with a certificate of calibration, it did the same thing there where it found the 220 volt. That was the measurement uncertainty off the certificate of calibration. So it grabs all of those values back and calculates the total measurement uncertainty. And then they have this set to a K equals 2, but you can use different values. So does that answer your question?
Yeah. I was just wondering, that spreadsheet is just for DC volts, so you're going to end up with a number of spreadsheets for each calibrator.
Yeah, you could put it in. You could put in one massive one and then have this huge selection thing. But typically in the US, they're going to have a range for a calibrator. So you're either going to have a measurement uncertainty for each one of your ranges, or you're going to have a measurement uncertainty for a function in a generator, and then several different spreadsheets for each one of the disciplines. All right, so the next thing I want to move into is now that we've got our measurement uncertainties, our spreadsheets up there, when we're doing manual calibrations, we can also do the same thing there. So we can type in a measured value. If we hit the little plus button here, that'll allow us to put in multiple values. So we could put in, it read 10 volts, it read 10.0002, read 10.0006, it read 9.9995. We could put all of those in, and the manual calibration will also calculate the repeatability and send that value into the measurement uncertainty calculator. And the measurement uncertainty calculators are available on this drop down, and you can see it actually calculate those in real time. Pull this up here real quick so we can see it. So each time I hit that, it's calculating the mean value. It's calculating the repeatability of the resolution. And now if I hit save, it's going to send that back in here. And if I want to see my measurement uncertainties using a 5720, or I'm sorry, using this measurement uncertainty calculator, I can grab it. It'll pull it down and calculate it. And if I want to see the measurement uncertainties with the metrology ERP, it's going to grab that value, calculate it, and bring it down. So you can see each one of these calculators I've got from customers have slightly different things that are inside of their uncertainty calculators. And then if I hit save, it's going to come back in, calculate the TUR, the confidence, and the false accept values. So all of that gets done automatically on the fly. But that's how it'll come back in and dynamically calculate your measurement uncertainties as you're running. So the next part of this is going to be a little bit of a homework. If you come out to these sites out here, so in CalLab Magazine back in 2015, we wrote an article on how you can do dynamic measurement uncertainty calculations with any software. Later, we came back in and wrote another one that you can see out here on CalLab Magazine on this site. And the CalLab Magazine site, we're talking about specifically how you can use Fluke MetCal and callmetrology.net to calculate your measurement uncertainties from Fluke MetCal. So now you can do one modification to your procedure in MetCal, call metrology.net to do your uncertainties. As your uncertainties change over time, you don't have to go back in and make tweaks to your MetCal procedure to handle the changes that are going on in your higher end calibrations. So I think we've covered all of the learning objectives in here. So talked not so much about object-oriented programming, but inside of that results object, as you add in the measurements, all of those calculations, that resolution and repeatability, are handled by that object. So you don't have to come back in and code that special each time. The object knows how to do the work with that data. Covered how the measurement uncertainties are in the drivers, covered the resolution, repeatability, how you format the spreadsheets, and then how you can upload the spreadsheets into metrology.net. So any general questions?
Hey, Mike, this is Scott.
Hey, Scott.
Hey, I noticed that Fluke usually has an absolute specification and a relative specification. I mean, is the relative specification supposed to be for if you want to throw in your own uncertainties from the equipment used to calibrate it with, or how does that work?
Hey, Mike, this is Jack Soppy. Can I make a quick point here?
Yeah.
Yeah, I dealt a lot with Fluke over the years, and I'm sorry to get in late here. Got in right at the end, I guess. The relative specifications that are on a Fluke calibrator or precision instrument spec sheet are all the variations for time, stability, linearity, everything, but they do not include the uncertainty for traceability, because some labs don't have the same minimum uncertainty on the standards as is required to give maximum performance. So it's the total performance without including any uncertainty of the calibrating standards or the uncertainty of the calibrating process. So that's why it's relative, and that's important in many European countries and things like that, and Asian countries, because they're in an area where their national lab might be a little different. Does that make sense?
Yes, it makes sense. My question is, if, say, for instance, I'm running a test process like a 3458 reference to a 10-volt cell, I mean, that tightens the uncertainty right there.
Yes. So if you're using the 10-volt cell to characterize a 3458 or calibrate a 10-volt range on it, then you've got basically, as you're using it in a short period of time, in the same temperature in a lab environment, you know, the variation of uncertainty is very small compared to what it is on a 1 year, 90-day, or whatever spec that you have otherwise. And I don't have the numbers for 3458 in my head. And they cut and slice their numbers similarly, but a little differently too. Fluke's relative numbers fits into the ratio measurements. And if you want to take a look at the ratio style measurements, a ratio measurement really is only a variation for short term within a range of a particular instrument. And that's also a very good uncertainty to use when you're adding the uncertainty of a 10-volt standard to the overall measurement of 10 volts and things like that. And there's ways that in the 3458 application notes that they describe that process. I just don't know it off the top of my head.
There's something new about the relative spec, because I thought they were looking at the drift and stability if you referenced it against something in your lab.
Yeah, if you take it and add that, have that relative, and then take your calibrating standards and calibrating process and RSS that together, it isn't a straight addition, because an RSS is the practical accepted way to combine multiple uncertainties like that, and they are independent, the uncertainty on that. So you don't add it together, you RSS it together in most cases.
That makes perfect sense. So any other questions?
I'm good. Thanks, Mike.
That's pretty much it for me. That was my one big question.
So, all right, well, I appreciate everybody coming into this automation lunch and learn. And